Right, for today we will be discussing the magnetic method. Now let's have a brief history. In the 1600, William Gilbert published a book on the concept of the Earth's magnetic field, all right, which actually varies or has a definite field orientation at every point in the Earth. Okay, so this concept of magnetism or geomagnetism was described as early as 500 years ago, or rather 400 years ago, sorry. And then 40 years later, we had the early compasses in Sweden that are used for iron ore prospecting. So actually take note that the iron ores or the magnetite ores in Sweden are strongly magnetic, right? So it was a no-brainer back then for the Swedes to use compasses for iron ore prospecting. Okay. Later, 230 years later, you have Thalen constructing an early magnetometer, which can actually determine the horizontal component, vertical component, and the declination or the orientation of the magnetic field for a given point. And then later on, we have Adolf Schmidt constructing a precision magnetometer, right? And from there on, there was a rapid pace of development of magnetometers, right? Being used in different applications, including small metal objects, right? Now, for the first concept, let's talk about what is a magnetic flux density, which is indicated by the letter B, capital B. And magnetic flux density is also called magnetic induction. So you can imagine magnetic flux density as a counterpart of electrical current, right? So you have here a movement of of okay, so you have a movement of energy due to magnetism. Right now, this magnetic flux or the magnetic equivalent of electrical current is typically is measured or can be measured per unit area, okay? And which is called magnetic induction, right? And this can be calculated as a function of mu or the absolute magnetic permeability of your medium or your material, and this is in units of ohm per second, or rather ohm second per meter, multiplied by capital H or your magnetic field strength, which is expressed in ampere per meter, right? Now, take good note that the absolute magnetic permeability of your rocks and soil is related to the magnetic susceptibility, which is an intrinsic property of rocks and soil. But to be precise, it is a function of the mineralogy of your rock and soil. Alright, so we will be discussing the concept of magnetic susceptibility later on. Now, to continue, magnetic flux in system and international units or in our standard international units is expressed in volt second, which is also called Weber. Now, the unit of magnetic flux density or B is expressed in volt second per cubic meter or also Weber per cubic meter. And incidentally, this is also called Tesla, right? Tesla after the Eastern European American inventor Nikola Tesla, not the brand of car. Anyway, also take good note that in practice, magnetic fields that we measure in the field are flux densities, right? So that's you're technically measuring the quote unquote magnetic current per unit area in the field. Now, Tesla is too large as a unit, all right, and it's actually more convenient or practical to express flux densities in terms of nanoteslas, or basically teslas divided by a billion, right? Now, to add confusion, magnetic flux density, or B, is what's being measured by our magnetometers in the field. And now, it by the geophysics jargon, we typically tend to call magnetic flux density as magnetic field, right? Which is technically magnetic field is totally different from magnetic flux density. Okay, so when you see the term magnetic field in the context of field survey, they are normally or typically referring to the magnetic flux density. Right now, going back to the absolute magnetic permeability, or the mu of the most important material, which is, or rather non-material, which is vacuum, or for practical purposes, air. Alright, so it has a value of 4 pi times 10 raised to the negative 7 ohm second per meter. And this is a important value, and we denote it by the symbol mu naught. Now, to continue with the other concepts, let's talk about relative permeability, or mu sub r, susceptibility, or K, and magnetization, M. Right now, magnetic permeability of other medium like minerals, or rather other medium aside from vacuum, like minerals, soils, and rock, can be expressed relatively, all right, relatively as relative permeability, or mu r, or as magnetic susceptibility, K. Right now, both numbers are dimensionless. Okay, so we can look at magnetic flux density. All right. Uh, Now note that magnetic flux density, or by jargon magnetic field, is modified by magnetization, or the response of a material. So to make it sound more simple, all right, when you have a magnetic field, all right, of the Earth, okay, so the Earth has a magnetic field, and this magnetic field will be modified depending on what material or medium is interacting with that magnetic field. Okay, so you have a response when the magnetic field is interacting with vacuum, and you also have a different response when your magnetic field is interacting with rocks and soils of different magnetic susceptibility or different relative permeability. Okay, so when you are using relative permeability, or mu r, okay, you can express the magnetic response of your material, okay, or you can calculate the magnetic response as magnetic flux density by multiplying your mu naught, or the permeability of vacuum, times the relative permeability times the magnetic field, or H, right? Now, if you are using the magnetic susceptibility term, or K, all right, you can calculate the magnetic flux density by basically adding the magnetic flux density due to your material to the magnetic flux density uh, of your vacuum. Okay. Hence, magnetic susceptibility is basically just your relative permeability minus one. Okay. Right. Now, again, okay, note that, or to emphasize, your medium always imparts an additional field strength. Okay, when it is responding or is interacting with the Earth's magnetic field. Okay, so this is basically the response, or the magnetic flux density that is being generated when your material is responding to the Earth's magnetic field. Okay, now we call that quantity magnetization. Okay, so magnetization is basically the response of your material. Okay, which is basically this is supposed to be mu r. Oh, sorry. So magnetization is basically big M is equal to mu naught times the magnetic field H times magnetic susceptibility. Okay, so that is basically the response, okay, additional response due to your material reacting with the Earth's magnetic field. And this is typically expressed in units of ampere per meter. All right. Note that all these values are typically expressed as vectors. Okay. So in magnetic methods, direction is important. Okay, because magnetic field has a polarity. Okay, it has a positive and negative directions. Now, just to summarize the important values, we have total magnetic flux density, which is also called total magnetic field or intensity in the geophysics jargon, and this is indicated by the letter B sub t. We also have vertical component of the magnetic flux density, or basically the vertical component of your magnetic field or intensity, and we also have the horizontal component, okay, indicated by B sub h. Okay, so we have B sub t, B sub z, and B sub h. Okay, so the vector summation of B sub z and B sub h will get you your B sub t. Now, there are more concepts here. Let's talk about magnetic moment. Sorry, I hate talking about concepts, but this can hardly be avoided in magnetic methods. Okay, so please bear with the discussions. Now, so going back, let's talk about magnetic moment, magnetic dipole, and remnants. So, okay, so once you start talking about a material with a given volume that is being magnetized or is responding to an external magnetic field, okay, that has a given intensity m, okay, so it will have a moment, okay, or a sort of a magnetic momentum. Okay, so your momentum in physics depends on your, is it velocity times the mass? Okay, so it's sort of dependent on the energy and the size of the object. So the same happens with your magnetic moment. Okay, so your magnetic moment, small m, is a function of your volume of your object and the intensity of magnetization. And this can also be conveniently expressed as volume times magnetic susceptibility times the strength of the magnetic field, or the magnetic field, or the external magnetic field, right? Now let's move on. We also have another concept called dipoles, which are basically atoms with magnetic moments, although all atoms basically have magnetic moments, although they have different values of magnetic moments. Okay, and note that going back, magnetic moments are vector quantities. And now a dipole has a magnetic moment. Okay, so basically a dipole looks like this. So you have your atom here, and it will basically have a positive and a negative polarity. Okay, and yeah, it has a moment m, small m, and it will have a direction. Right now, note that certain bodies or certain materials are actually magnetized even in the absence of an external magnetic field. Okay, and this is what we call remnant magnetization or remnants. Okay, and remnants actually stacks with induced magnetization. Okay, and another feature of remnants is that it can be imprinted on a body, or a body can be magnetized by exposure to an external magnetic field. And also remnants can be erased, okay, from an opposing external magnetic field. Okay, it's sort of a, so any object can basically sort of act as a, or can sort of record, okay, its exposure to an external magnetic field. And we will be discussing that later in detail because there are a lot of types of remnant or remnants. Okay, now let's talk about the magnetic properties of your rocks. Okay, so there is an emphasis on rocks because magnetism is highly influenced by mineralogy, and rocks in particular, okay, have minerals. So technically you also have soils, but most of the minerals that have significant magnetic properties are found in rocks. Right? Now, to put things in context, magnetic survey methods need an accurate measurement of your magnetic anomalies or contrasts in magnetization. Okay, so sorry, I have a shit handwriting. But going back, okay, so you're looking for differences in magnetization in a particular area. Okay, and this is mostly due to the differences in magnetization of your rock formations. And consequently, the magnetization of your rock formations are basically a combination of two factors, which we have just discussed earlier. So first is your induced magnetization or the response, where is it? Or basically induced magnetization as the response of your material to the Earth's magnetic field. And the second is the remanence, all right, of your material, or the independent magnetization of your material, which is basically a product of geologic history, as you will see later on. Okay, so the magnetization of rocks, okay, can be due to an external magnetic field. It can be also due to its own magnetic field due to remanence or due to imprints, which is a product of geologic history. Okay. Now let's talk about the magnetization due to or due to the Earth's magnetic field. Okay. So how a rock would respond to the Earth's magnetic field will depend on its magnetic susceptibility. Okay. And the magnetic susceptibility of your rocks, okay, are dependent on the mineral, or basically dependent on the mineralogy. And we have a lot or types of minerals of different magnetic susceptibilities, which can be categorized as diamagnetic, paramagnetic, ferromagnetic. Okay? Now, let's start off with diamagnetic materials. Basically, or to laymanize things, diamagnetic materials actually hate the Earth's magnetic field. Okay, so whenever they are subject to the Earth's magnetic field, they sort of generate a shield which neutralizes the Earth's or the external magnetic field. So you get more or less a reduction of the Earth's magnetic field. Okay, so what happens here is basically these materials have a negative magnetic susceptibility. Okay, so magnetic because they reduce the Earth's magnetic field when they are interacting with the Earth's magnetic field. Okay, because they oppose. They basically create a magnetic field that opposes the external magnetic field. Okay, so yeah, you get a net reduction in your magnetic field strength, and consequently, you get a net reduction in the magnetic flux density. Now, how this works is consider an electron. Okay, so an electron basically orbits its nucleus or the nucleus of an atom. Okay, now electrons Okay, when they are exposed to an external magnetic field, okay, what they do is they actually try to create a magnetizing force that will oppose that external magnetic field. Okay, so this process is present in all materials. Okay, and this is what we call the Larmor Procession. Okay, so basically, electrons, when they sense an external magnetic field, they try to revolve such that they will generate a magnetic force that will oppose the external magnetic field. Okay, so this phenomenon is present in all substances. Okay, but not all materials have a net diamagnetism. Okay, so remember that the magnetic property of materials is always a summation of all its components. Okay, so you typically have, so even your classical strong magnetic substances like iron, cobalt, and nickel are actually have a mild form of diamagnetism. Okay, but they tend to be cancelled out or uh, dominated by its strong magnetic susceptibility. So anyway, what we are only concerned here is materials that are net diamagnetic. So you have quartz, marble, graphite, rock salt, and anhydrite as our typical diamagnetic minerals. Okay? And these minerals are net diamagnetic, okay? Basically because they have because their diamagnetism is not being cancelled out uh, by other magnetic forces within the mineral, okay, which is due to their zero magnetic moments because they have an even number of outer electrons. Okay. Now let's talk about paramagnetic substances. Okay. These materials have a positive susceptibility, meaning when they are exposed to a magnetic field, they actually increase the external magnetic field. Okay. Now, the important feature of paramagnetic minerals or paramagnetic rocks is that when you heat them up, okay, when they are exposed to heat, what happens to their magnetic susceptibility is that the susceptibility actually goes down. And the main reason why their susceptibility is reduced by high temperatures is that high temperatures actually prevent their dipoles from aligning to the external field. Okay? Basically, high temperatures cause your dipoles to jump up and down, bounce around, and so on. And because they're bouncing around and playing around due to high temperatures, they are actually unable to align to the magnetic field, okay, and actually increase that external magnetic field. Okay, so high temperatures sort of randomize their alignment instead of allowing them to uh, contribute to the external magnetic field. And paramagnetism is actually sort of a property that is caused by impurity of your rock. For example, you have rocks that could be paramagnetic due to weak ferromagnetism, due to impurities, or due to mineral impurities containing magnetite or ilmenite, or this can also be caused by anti-ferromagnetic minerals like hematite and manganese dioxide. Now let's move on. Ferromagnetism. These are okay. So magnetic minerals or materials are have strong interactions with the external magnetic field, and you basically have three types. First is the truly ferromagnetic. Okay, but this is basically just a hypothetical rock. Okay, uh, truly ferromagnetic materials are pure iron, cobalt, and nickel materials. Okay, but you don't have these materials as rocks, so these only exist as artificial substances. So truly for ferromagnetic materials basically have atoms, okay, and their atoms or their dipoles actually sort of love to form or align into to certain regions. Okay, so basically these are, if you're talking about people, these are people that like to live in villages and they unite. Okay, they have a strong front. So these atoms basically tend to band together and form domains. Okay, so these domains ha consist of dipoles or atoms that are banding together, and they basically have a certain alignment, so they align in one direction, which allows them to stack together their magnetic moment. Okay, so they have a huge magnetic moment, and yeah, so they tend to strongly interact when there is an external magnetic field. All right. Now you also have anti-ferromagnetic. Okay. Now what happens in anti-ferromagnetic is you still have atoms or dipoles that are banding together, but instead of having dipoles that are going in one direction, you have dipoles that are banding together, but they align opposite to each other. Okay. So what happens here is that you are actually getting a net zero magnetic moment. Okay. And the best example here is your hematite. Now we also have ferromagnetic rocks or minerals. Okay. And these involve dipoles or atoms that are still banding together. All right. And they also have counterpart dipoles that are opposing each dipole. Although the difference here is that typically the opposing dipoles are smaller. So there you're actually having an imbalance here of magnetic moments. And this of course results in a net positive magnetic moment, which results in a high magnetic susceptibility. Okay? So Basically, the materials here with the strongest magnetic susceptibility are your truly ferromagnetic materials. But there's no such thing as pure iron, cobalt, or nickel rock. So these uh these things don't exist as rocks. Now, the second strongest ferromagnetic materials are your ferrimagnetic rocks or minerals, which include rocks or pure minerals of magnetite, titanomagnetite, and ilmenite. Okay, so they have magnetic moment. They have a non-zero magnetic moment, and then the weakest in this group are your anti-ferromagnetic, which have basically zero magnetic moments due to equally opposing dipoles. All right, now let's talk about the magnetic susceptibility of rocks. Okay, so in this case, the magnetic susceptibility of rocks are basically almost solely controlled by the amount of ferrimagnetic minerals like magnetite, ilmenite, titanomagnetite, okay, as well as how much minerals do you have, how are they distributed, what are their sizes, and so on. So the magnetic susceptibility of rocks tend to be highly or extremely variable, and this is quite clearly reflected in this chart. So a pure magnetite will have a magnetic susceptibility of as high as 15 million. Okay, so magnetic susceptibility is a dimensionless number. So remember, it's a dimensionless number, so we don't have units here. So you have magnetite going as high as 15 million. You have like basalt going as high as 1,500 to 25,000. And then you have these diamagnetic materials like graphite, quartz, and hydrite, marble, dolomite, which have negative susceptibilities. Okay, so these materials or minerals or rocks oppose any external magnetic field, right? So going back again, these numbers are extremely variable, and this chart is only just a good guide or just a good guide for getting the approximate numbers of their magnetic susceptibilities. Now let's discuss further the concept of remnants or remnant magnetism. As discussed earlier, remnants or magnetism is a product of the geologic history of your rock or mineral. Or rather, it's a product of the geologic history of your rock. And there are various ways in which you can get remnant magnetism in a rock. First is your thermoremnant magnetization or TRM. And this is basically caused by the process of cooling from high temperatures. Okay. So what happens here is when a magma is cooling down, okay, and the threshold temperature is approximately 600 degrees Celsius, which is the Curie point of magnetite. So once your rock or your magma hits 600 degrees Celsius or cooler, it actually starts forming magnetic domains. Okay? Particularly if your rock contains magnetite, titanomagnetite, or ilmenite, or other ferromagnetic minerals. So it starts to form magnetic domains, And the orientation of your domains will always be a function of the prevalent geomagnetic field at that time. Okay, so it will always record a snapshot of the geomagnetic field at that moment and at that place. Okay, so remember that the Earth's magnetic field is not fixed, it's not stationary, it's always changing approximately every 500,000 to 1 million years. Okay, so as a consequence, you can expect different magnetic orientations in rocks, okay, every 500 to 1 million years due to thermoremnant magnetization. Now, the other way to get remnant magnetism is by exposure, okay, by constant exposure to a magnetizing for, or rather, by exposure to a magnetizing force for a short period of time under a constant temperature. Okay, so basically, as by exposing a material to a magnetizing force, a strong magnetizing force, you can impart remnant magnetism on it. Okay, and another is viscous remnant magnetization, or VRM, and this is all about a long exposure to a magnetic field. And finally, you also have two other means to get remnant magnetization. One is your detrital remnant magnetization, which happens when your sediments, which contain magnetic grains, are being deposited in water. And as they are depositing, okay, so if this is the magnetic field of the Earth, what happens is the grains also will tend to align to the magnetic field of the Earth. Okay, such that when they settle down, you basically have a set of magnetite or ilmenite or titanomagnetite grains that are aligned to the magnetic field at the time of deposition. Okay, and now the last type is chemical remnant magnetization, which is basically all about recrystallization of magnetite grains at low temperatures. Okay, so as they are recrystallizing, they will essentially reorient, okay, to the current magnetic field. Now let's talk about the importance of remnants. Okay, so remember that the total magnetization of rocks is a combination of induced magnetization, which is a function of magnetic susceptibility or the mineralogy, times the intensity of the Earth's magnetic field. And you also have remnants, which is basically a recorded magnetic strength from the geologic history of your rock. Now, note that remnants can be actually very strong. Okay, there are times where remnant magnetism is actually stronger than your induced magnetization. Okay, so these can actually signal an interesting geologic history. Okay, if you so these can indicate an interesting geologic history, and we can find these materials by the use of the Konigsberger Ratio, or Q sub n, which is basically the ratio of the magnetization intensity due to remnant magnetization versus the intensity of magnetization due to induced magnetization. So the bigger the ratio, the bigger your remnant magnetization is. Okay, so any number that is greater than 1 means that the remnant magnetization is very strong on that rock and might be signaling a interesting or anomalous geologic history. Okay, so these are the typical Konigsberger ratio for some rock specimens in different areas. Okay, so you have in Japan, Scotland, Sweden, Japan, okay, Madagascar, Switzerland, and so on. Okay, so you can note that these are very high permanent magnetization, while others are having low values. Now let's talk about the geomagnetic field. Right, sorry for the interruption. Now the Earth's magnetic field, or its mean or regular or undisturbed magnetic field, is important to be known. All right, because it serves as the reference number in which we determine if there is a sudden increase or sudden decrease in the magnetic field. And that's what we call anomalies. Okay? So we have to know, it's important or it's essential to know the undisturbed or the expected geomagnetic field of the Earth. Right? Now, okay, so in terms of orientation, okay, you can basically imagine the magnetic field of the Earth as a point dipole. So this is your dipole, and your magnetic south is, of course, in the South Pole, and the north is in the North Pole. And basically, all the vectors are headed to the South Pole. Okay. All right. So all the magnetic vectors are going to the South Pole. And all right. So in terms of the magnitude of the magnetic flux density, they typically vary from 20,000 nanoteslas to 60,000 nanoteslas. All right. And in terms of coordinates or components, magnetic flux density vector is specified by the following parameters. You have your horizontal component of your flux density, or B sub h. You have your vertical component, which is B sub z. And note that, okay, so B sub z is positive if it's pointing upwards, as in the case of the northern hemisphere. Okay, and negative if it is pointing downwards. Okay, so note that in the north, your uh, flux density vectors are sort of exiting the Earth. So they're exiting, so they're pointing upward. And then once you reach the South Pole, they are sort of entering again the Earth. So they're pointing downward. Another component is your declination, D. of the flux direction, which is expressed as degrees, right, relative to the true magnetic north. Okay, so declination is just sort of a uh, bearing, okay, or the direction of the flux density. And finally, you have inclination, right, or basically the ratio between B sub z and B sub h. Okay, it goes from 0 to positive 90 to negative 90. Okay, so this is basically the dip, right? This is basically the dip of your magnetic flux density vector. Okay, so in the magnetic north pole, your inclination is purely vertical and pointing upward, so your inclination is positive 90. And then in the south pole, your flux density is basically is vertical and pointing downward, so it is negative 90. Okay, in the equator, your density is almost horizontal, so you get inclination equal to 0 degrees. It's purely horizontal. All right. Further notes, in surveying, diurnal variations or the daily variations in the Earth's geomagnetic field are important, and also you have magnetic storms from the sun, which are quite random and should be eliminated from your magnetic survey data. Now let's talk about the instruments. You have what we call the flux gate magnetometer, and basically this involves rings and wire coilings. And these are the two important components of the flux gate magnetometer. You have your drive winding and you have your sense winding. So this is your drive winding, this little ring over here. And then the drive winding is actually being enveloped by a bigger ring, which is what we call the sense winding. Okay, so a drive winding is basically a ring, which is this one, and you have coils or wires coiling around your ring. And basically, they have two important halves. You have your blue part and your green part here to denote the two important halves of your drive winding. Okay, so these two halves react or amplify the external magnetic field. Okay, and they only react to a specific direction of of an external magnetic field as indicated here. Okay, so they only react to a specific component of the magnetic field of the Earth. Okay, so it could be positive, it could be horizontal, or it could be the vertical component. Okay, so that's the important feature of a flux gate magnetometer is that it can separate the Z and the H components of your magnetic field, or rather the magnetic flux density. Okay, all right. Now your sense winding is basically the sensor of your magnetometer, and it is just wrapped around or outside the drive winding. So it is supposed to detect the response of or the amplification done by the drive winding. So now when the flux gate magnetometer is in operation, all right, so when the equipment is operating, the drive winding is actually being supplied with an electrical current, okay, from the instrument itself. and the current will actually uh, force the two halves to generate a magnetic field. Okay, so the green half will generate a magnetic field that is in the same direction as uh, the supposed direction of the external magnetic field, or its sensing direction. Okay, so it will generate a magnetic field that is parallel to the direction of the sensing direction, and then your blue half will create a magnetic field that is opposite the sensing direction. Okay, and so there you have basically opposing magnetic fields, right? And when there is no external field, or you have zero external field, or theoretically you have a zero external field, the magnetic fields being generated by the two halves are pulsing pulsing in sync, or they are synchronized. So these are pulsing together and they're synchronized, but they go in opposite directions, and their strength is equal. So they have equal strength. Okay? And what happens is that their magnetic fields just cancel out, as you can see here in this plot. So I have a field pulsing in the positive, negative, positive direction, and you have basically an opposing field, and they basically cancel out, such that the sense drive will not detect anything at this condition. However, when there is an external field present, or when you have a non-zero external field, okay, so what happens is that the magnetic field generated by the two halves change. Okay, so the half that is acting opposite of the sensing direction will have a peak that is lower. Okay, for example, this blue peak will be lowered. Okay, instead of having this a peak at this point, it will peak out at this position. Okay, while the other half will peak at a higher value. Okay, so their magnetic fields will not cancel out anymore, and there will be a net magnetic field being generated by the two halves. Okay, and this net magnetic field will trigger an electrical current in the sense winding. Okay, so this will trigger a current in the sense winding, and the strength of the current will be just proportional to the strength of the external magnetic field. The other type of instrument is what we call the Proton free precession magnetometer. And the main principle behind it is that the protons in all atoms are spinning in an axis that is aligned with the magnetic field. Okay, so these protons, alright, always tend to line up or align with the Earth's magnetic field. But you can disturb that. Okay, so you can always disturb that alignment by inducing a, by inducing or generating another magnetic field, okay, through the instrument, okay, such that the proton or their axis of spin will align with the artificial magnetic field. Okay, Now, once you turn off this artificial magnetic field, the protons will revert back to their original alignment, okay, which is the magnetic field in the site. So as they realign, or as they return to their previous alignment, what happens is they tend to wobble, or they precess like a gyroscope or a Beyblade or a trump, depending on your age. I don't care. But for illustration purposes, this is a gyroscope, and you can see it wobbling as it is spinning. Okay, so it wobbles a bit as it goes around. And what's important in the proton precession is how many wobbles per second is occurring, or the frequency of the wobbling or the precession. Okay, and basically, the more wobbles you have, the stronger the Earth's magnetic field is. Okay, so basically, a strong magnetic field will force your protons to wobble faster until it realigns to that magnetic field. The other type is the alkali vapor magnetometer, or the cesium vapor magnetometer. This basically or typically consists of a cesium vapor in a glass bottle, and it is being continuously being lasered. Okay, okay, so you have a pump laser here, and the pump laser is causing the cesium vapor to emit photons. Okay, so it emits photons. And you also have here a probe laser, which is paired with a detector that is continuously monitoring the visibility of the cesium vapor. Okay, so it is quantifying the visibility of the cesium vapor. Okay, and while the vapor is being continuously lasered, it has a high visibility. But once it is exposed to the external magnetic field, the state will be disrupted, and this will change the amount of photons being emitted, and it will change the visibility of the vapor, and this will be detected by the probe laser, which is paired with a detector. Okay, and the amount of disturbance is related to the strength of your external magnetic field. Okay, just to have a quick comparison. All right, all these types are relatively portable. Okay, and they can be actually deployed in boreholes, underwater, ground survey, or airborne whatsoever. Although they have differences in terms of accuracy. Okay, flux gate practically will have a accuracy of 5 to 10 nanoteslas. Okay, but it can go as precise as 1 nanotesla. Your proton magnetometers can go as precise as zero point 0.1 to 1 nanotesla. And then your alkali vapor, which is the most accurate, can go as far as zero point zero 0.01 nanotesla accuracy. Now, one of the key things to note here is that the flux gate type of magnetometer is the only type of magnetometer that can measure the components of your magnetic field. Okay, so it can measure the horizontal and the vertical component. Okay, so let's proceed to the survey types. All right, so surveys are generally concerned with getting the total magnetic field of your area and then subtracting out the magnetic field due to the Earth. Okay, so what the difference that you get can be either positive or negative. Okay. So when you have a positive difference, it means that the magnetic field is higher than expected. And when you have a negative difference, you have a field that is lower than expected. Okay, so these are called positive anomalies and negative anomalies respectively. Okay, and they are basically due to variations and presence of different objects in your Earth's crust, which can range from World War II bombs, metal pipes, ore bodies, geologic formations, and so on. Okay, and speaking of expected geomagnetic reference or geomagnetic field, we have what we call the International Geomagnetic Reference Field, or the IGRF, which is basically your baseline number for the expected value of the Earth's magnetic field for a given time and location. Okay, so this is a mathematical model of the Earth's magnetic field. Okay, so it only accounts for the main magnetic field of the Earth, meaning it doesn't care about the crust. Okay, it's all about the magnetic field of the Earth, which is mainly arising from its electrical convection currents inside the Earth. And you can use this data set to subtract out the magnetic field of the Earth from your magnetic field survey data so that you can get the magnetic anomalies. Okay. Now, note that the output of this model is quite detailed, so you can get declination, inclination. Okay. You also have your intensities in different directions, like north, east direction, horizontal direction, vertical direction, as well as the total intensity. Now, speaking of anomalies, you also have a global data set, which is called the Earth Magnetic Anomaly Grid. And this is basically a data set of the whole world showing the anomalies for the whole Earth. Okay, so this is an anomaly map. Okay, so this is already processed data, and most of the stuff that people do with this data set is to just interpret this data and compare it with other studies like geologic mapping, all right, and other sorts of geologic information. Okay, although note that this dataset has an approximate resolution of 2 kilometers. Okay, so each pixel is approximately 2 kilometers in size, which makes it good for regional mapping purposes. All right, and this dataset can be obtained from this website. Okay, now let's talk about ground surveys. Okay, ground surveys is one of the most common forms of your magnetic survey. And for geologic surveys or geologic mapping purposes, your typical survey layout will consist of survey lines that are spaced. Okay, so these are survey lines on a top view, and they will be spaced around 20 to 40 meters apart. Okay, and they are to be oriented perpendicular to the geologic strike, okay, of your geologic formation. Okay, so if this is your strike and dip symbol, okay, your so this is your strike. So therefore, the survey lines should be perpendicular to your strike. All right, now when you are dealing with detailed geologic surveys, which is I think important in exploration activities, your line spacing may be as close as every 1 to 2 meters. Now there are rare circumstances or there are some circumstances where magnetic surveys are employed in engineering and environmental applications. Okay, I could think of World War mapping out or detecting World War II bombs in an area, or unexploded ordnances in general, looking for metal pipes, okay, or even treasure hunting. This the line spacing will be small and it will be depending on the size of the target object. So, for example, if you're looking for a bomb, a World War II bomb that might explode, so for example, you're doing construction work and you're scared that your construction activities might hit this World War II bomb, and you want to find it in this area and you want to remove it from your site, and you know that its length is 2 meters and its diameter is around 1 meter. Okay, so ideally your survey line will be spaced less than 1 meter apart. Okay, for maximum chances of detecting the object. All right. All right. Now, other notes. During survey, your clothing actually matters, and as well as your accessories. So keys, pen knives, anything metallic like wristwatches, and any other metal objects like steel-toed boots can interfere with your instrument. Okay. So metallic and magnetic objects are basically not allowed during a magnetic survey. And another thing to plan for is the daily variations or within the day variations in the Earth's magnetic field. Okay, or what we call the diurnal variations. And these are accounted for by either of these three methods. One is by having a second magnetometer on a reference station, and you have that magnetometer continuously measuring the magnetic field at that point. So you have a reference of how the magnetic field is changing throughout the day. Second option is, all right, now continuing, you also have your airborne surveys, okay? And don't have much to say here, but airborne surveys are typically done at altitudes of 70 to 200 meters in height, or it could be lower. So if you are interested in an increased data resolution, and typically the flight paths of the airborne survey should be intersecting. Okay, so in here you are having intersections with the previous survey lines. And the purpose of this is to basically reoccupy or resurvey certain points so that you can do your diurnal corrections. Okay. Now let's talk about qualitative interpretation. Okay. And qualitative interpretation is very useful for regional mapping, and it all hinges on your delineation and recognition of patterns. And what we have here is a summary of the patterns, the descriptions of patterns, what they might look like, and the possible interpretations of those patterns. Okay, you have like circular features, which can be interpreted as intrusive bodies or even ore bodies. You also have long or elongate features, which could be dikes or intrusions and fractures in joints, tectonic shear zones. Okay, so shear zones are quite wide. They can be they have a significant thickness. Okay. You also have isoclinical folds, which involve axes and limbs that are sloping in the same direction. And you also have long elongate ore bodies. Okay. Other pattern are your dislocations or offsets, which can be interpreted as geological faults. Now we also have what we call sheets or high intensity or positive anomaly areas that are widespread. Okay, and this could mean basaltic flows, gabbro intrusives or large-scale gabbro intrusives. You also have greenstone belts. Although greenstone belts are quite specific, okay, so these are metamorphic rocks present in Archean to Proterozoic cratons. And finally, you have this what we call areas with little relief compared or areas with more or less almost zero anomalies. Okay, and this could be quartzitic rock formations, monzonite, limestones. Okay, although note that metamorphism in limestones, which can produce marbles and skarns, may typically have magnetite minerals. Okay, and they might not have this kind of low relief anomaly. Okay, so this is an example of a magnetic contour map. So this is basically uh, total magnetic flux density, but in the geophysics jargon, this is a magnetic field intensity map. And you can see here some elongate features. Okay, elongate features. I mean linear features. We also have elongate features. Okay, elongate features, and we also have some quiet areas here or low relief areas. All right, and this is what they're supposed to look like. Okay, so this is the formal interpretation of the area. So the elongate features are interpreted as granulite with magnetite. It could be also be a veined gneiss or intrusive body. The elongate feature here is interpreted as scar formation. Okay, we also have faulting in here. Okay, so uh, this interpretation obviously is not just based on the magnetic anomaly map. Okay, it's difficult to discern a scar from other kinds of features. So basically, this interpretation is also done in reference to an existing geologic map. Okay, so I think that applies to almost all geophysical methods. You don't just interpret based on on the geophysical data alone. You always do cross-checking with other data like geologic map, geologic field observations, drilling data, and so on. Okay, so it confirmation is always important in geophysics. Okay, now let's briefly discuss some methods in quantitative interpretation. And this is just a very quick discussion. So these are some of the methods used in quantitative interpretation. So one is the half width and the half slope method. So basically, this involves the use of geometric patterns in order to deduce the depth to your anomalous object. Okay. So basically, magnetic survey data can help you estimate the depth of your anomalous object. For example, or body, or World War II bomb. Okay, so you can basically estimate their depths based on the shape of your anomaly. Okay, but I won't be discussing that in detail anymore. Next is upward continuation, which is basically resampling of your magnetic anomaly map to get a coarser resolution. Okay, so this is, or the purpose of this is to enhance larger features or larger anomalies. Okay, for example, you're interested in the regional geologic formations, but you don't care about small scale variations in the rock type. So you can do upward continuation. And then you also have Euler and Werner deconvolution, okay, which is basically just a mathematical counterpart of the half width method. What we do here is we do mathematical calculations of the depth of your anomalous object when you know the shape of your anomalous objects, or you can assume what shape they are. Okay, so that concludes this lecture. Thanks for listening. If you have questions, you can message me. Okay. Uh, I guess enjoy the Holy Week. All right.